everyone. Welcome to the DIPS webinar titled The Importance of StereoNets and Kinematic Analysis as a Routine Method for Identifying and Evaluating Failure Mechanisms in Rock. Rocscience has been a leader in developing 2D and 3D software for civil, mining, and geotechnical engineering applications with over 20 years of experience and serving more than 8,000 users around the world. We have over 60 employees at our head office in Toronto, more than half of which hold advanced degrees in engineering. My name is Angela, and I'm one of the developers responsible for DIPS and several other rock engineering programs here at Rocscience. I'm joined today by Dr. Trevor Carter, who later in the presentation will provide some guidance on dealing with common problems people run into when using StereoNets, and in particular, pitfalls of statistical analysis of large amounts of data. Dr. Carter has a background in engineering geology and has been intimately involved with the development of the DIPS program code since its very inception, since he was Mark Diederich's external advisor for his master's thesis on the development of the original DOS version of the code. Dr. Carter has spent the majority of his almost 50 years career in geological engineering with Golder and is still on retainer to the mining and rock mechanics group there. But now in partial retirement, he is mainly involved in a review board role with, amongst others, the World Bank and several other major mining companies. Today's webinar will be broken up into two sections. For part one, I will focus on introducing the DIPS software, including a brief overview of key program features and demonstration of new features introduced through Maintenance Plus. For part two, Dr. Carter will be showing us how to interpret orientation data from a StereoNet. Specifically, we have some applied examples, which will cover the following topics: uses and abuses of StereoNets, some advantages and limitations, contouring issues, in particular set identification, oriented core and data reliability issues, dealing with too much or too little data. If you have any questions, please feel free to type it in the chat. We will also dedicate the last 15 minutes for Q&A at the end of the presentation. Before we start any kind of analysis, we need to know some basics about the geology of the site, such as the orientation, length, and spacing of discontinuities. And since not all discontinuities are made the same, it is also useful to keep track of rock mass strength and joint parameters. DIPS is a useful tool for helping us identify, visualize, and analyze these key characteristics of discontinuities. DIPS is a stereographic projection program used for the analysis and presentation of orientation-based data. The key features of DIPS includes the grid data, for which individual orientation measurements are input into the program, traverses on which the orientation data is recorded, and the StereoNet view to visualize the orientation data. In a rosette plot, we can visualize the radial strike or dip frequency of our vectors. And aside from allowing the user to look at structural data following the same techniques used in manual StereoNets, DIPS also has many computational features, such as sets and set statistics, jointing analysis, fold analysis, qualitative and quantitative attribute analysis, and finally, kinematic analysis. When you open a new DIPS document, the first thing you'll see is this spreadsheet called the grid data view. The grid data contains one row per plane measurement recorded as either dip direction, trend plunge, strike dip, or alpha beta. The grid data also contains information about the traverse and set that the recording belongs to, along with optional fields for distance and quantity. You may also add additional columns of data to the right of the predefined columns. Traverses in DIPS are lines or surfaces of known orientation on which joint or discontinuity data has been collected. These lines or surfaces can either be linear, planar, or curved. Some examples of traverses include scan lines, wall mappings, and boreholes. Traverses are used in DIPs for the following 4 reasons: keeping a record of which measurements were taken on each traverse, processing oriented core data from local alpha-beta angles to real trend plunge, applying Terzaghi weighting to correct for measurement bias, and finally, you will need the distances of each recording along a traverse to conduct spacing, frequency, and RQD analysis in DIPs. After we are done with the data entries, we can start visualizing our data and performing different types of analysis. One of the main features of DIPs is the drawing of stereographic projections, or StereoNets. In DIP's 2D StereoNet view, you can visualize orientation vectors, density contours, planes, intersections, and traverses, and add features such as sets, user planes, and various annotation tools. Sets are a useful way to group clusters of poles. There are several different options in DIPs to draw your set window: curved, freehand, circular, and sets from cluster analysis. After we finish defining our sets, we can obtain valuable stats info, such as the mean orientation and Fisher's K, which are automatically computed by DIPs. These values can then be used in limit equilibrium programs to define mean plane orientations and help with their statistical sampling. Also, if you have at least 2 sets defined, you may perform set versus set intersections in DIPs. Spacing analysis in DIPs includes joint spacing, joint frequency, and RQD analysis. Quantitative and qualitative analysis allows us to visualize and count how many poles fall into a certain grouping under one column of the grid data. We can visualize this either in a symbolic plot or chart format. Another key feature of DIPs is kinematic analysis. There are 3 main failure mechanisms which can be analyzed. They are planar sliding, wedge sliding, and toppling. With a given set of kinematic properties, i.e. the slope dip direction, friction angle, and lateral limit, we can see the critical zones for each type of failure mode along with the critical poles or intersections. We should consider kinematic analysis as a screening tool, but then turn to limit equilibrium programs such as rock plane, S-wedge, or rock topple to obtain a factor of safety or probability of failure. Also remember that we may need to take into account scaling, water pressure, and other shear parameters such as cohesion, which DIP's kinematic analysis does not consider. Now let me turn your attention to some new DIPs features since the introduction of Maintenance Plus. The View Settings template feature allows you to quickly save and load visual settings for the 2D StereoNet plots. In any 2D StereoNet view, you have these plot options and display settings in the sidebar, which allow for visual customizations to the plot, such as what to show and what not to show, colors, fonts, etc. This can be a little tedious if we want to apply the same settings to every StereoNet we generate. Using the View Settings template is simple. We first make the selections as desired in the 2D StereoNet view. Then we go to View, Save Template. Now we navigate to another 2D StereoNet view and we go to View, Load Template, and select the template we just saved. And now we should see that the changes are applied instantly. The most recent Maintenance Plus addition is the Import Wizard. In the past, if you wanted to input data into DIPs, you would likely have done so by copying and pasting columns manually from Excel. The Import Wizard allows you to efficiently import Excel data into the traverse information and grid data by simply specifying which Excel file you want to read from, what sheet in the Excel file, and the columns to import. When using the Import Wizard, you can optionally save the current selections as a template to be used later, when importing Excel data in the same format. And using this template manager, you can rename, delete, import, or export templates at a later time. Now I'd like to talk about the biggest addition to DIPS since its debut with Maintenance Plus, and that is filter options. The new filter options in DIPS allows users to work extremely efficiently with subsets of grid data. You can access the filter data dialog from the analysis menu or the toolbar. This dialog allows you to define conditional expressions used for querying columns of grid data, save multiple filters, and import and export filters. And just like DIPS version 7, you can still generate a new DIPS document based on the query by clicking the Create New File button. Once the filters are defined, DIPS computes and displays the results instantaneously upon toggling the filter dropdown in the toolbar. At the same time, the poles in the active filter are highlighted in the grid data view. What makes the data filter so powerful in DIPS is that it works on a per view basis. You can apply a different filter in each open view, which makes the side-by-side comparisons very easy. You can also apply filters to any view type or analysis type and instantly see the results. So all those features we talked about earlier, such as spacing analysis, kinematic analysis, StereoNets, charts, etc., can all be toggled to show either unfiltered or filtered results. The major advantage of working with filters is that you no longer have to create a new DIPS document in order to work with subsets of queried data, like with older versions of DIPS. This also means that you do not need to redefine traverse information, sets, and user planes. Any changes to the data will also be immediately reflected in the subsets of filter data. I have two examples which will showcase the import wizard, filter options, StereoNet plot, rosette plot, and kinematic analysis features of DIPS. In this first example, we will be looking at a data set which is in sedimentary rock and is heavily bedding dominated. And to start off, I have two Excel files containing borehole and discontinuity orientation data, which I will import into DIPS using the import wizard. We'll be starting from a fresh DIPS document. Go to File, Import Wizard, and under Data Types, we will check off linear traverse information as well as grid data because these are what we'll be importing next. So here we'll be importing the linear traverse information first. We'll open the Excel file that we want to import, which is in this borehole data. The sheet we'll be reading from is traverse list, and we will start reading the data from the second row to exclude the header in that Excel file. And under data to columns, here we'll set which column from Excel will be reading into which data header in DIPS. So for ID, we'll grab it from A. For trend, we'll grab it from B. And for plunge, we'll grab it from C. Next. Now we'll get the grid data. So again, I'll find the Excel file that we're reading from, which is contained in this discontinuity orientation data Excel file. And we'll be reading from discontinuity data sheet. And similar to before, we will start from row 2 for the first data row. And this time we also want to check off the distance column, and we'll be grabbing that information from the elevation column in Excel. And so similar process as before, we'll grab orient 1 from column A, orient 2 from column B, the traverse from column C, and the distance from column E. I also want to capture the feature column here, so I'll just create an extra column and call it feature. And we will grab that one from D. Next. In this import summary, we see that we will be importing linear traverse information as well as grid data. And the way that we're importing them is by overwriting. In this case, it really doesn't matter whether we're overwriting or appending, since we're starting from a blank document anyways. Under warnings, we see there are no errors or warnings found, so we should be good to finish the import. And here, optionally, we can save our current selections as an import settings template. And for demonstration purposes, I will go ahead and do that. And I will call this one demo 1 and finish. So you'll see the data is immediately imported here into the grid data, as well as in the traverse information dialog, all 98 of our linear traverses. And just to demonstrate to you how efficient it is to, instead of starting from scratch, to start from the import settings template that I had just saved, I'll just start from a new divs document again, and I'll go into the import wizard. And this time under template, I will select that demo 1 settings template that we just saved in the previous step. And as soon as I click that, the data types are automatically selected for us. Here, all we have to do is specify what file we're reading the linear traverse information from. So again, I'll click the same files as before. And you'll notice everything is automatically populated for us based on our selections before. Likewise, I'll do the same for the grid data import. And again, everything's pre-selected for us based on the settings template. And you should end up with the identical file that we had before for the import. So now let's take a look at the vector plot to see how this data actually plots. We see that poles exist all over the StereoNet, but that the majority of poles are near horizontal. This data is clearly very bedding dominated. Now, if we switch over to the contour plot, we can't see anything except the bedding. However, if we switch over to the rosette plot, it clearly shows that we have 2 orthogonal joint sets, which was not at all apparent in the contour plot. We won't be able to see the joint sets without removing the bedding in the center of the StereoNet because it is too dominating in the contour plot. So what we'll do is we'll go back to the contour plot and we will draw a set window around the poles in the middle using sets from cluster analysis. And we'll keep the maximum angle as 25 degrees and we'll select the approximate center of this cluster. Now that we've defined our set 1, let's go and try to filter out all the poles inside here using the filter options. So now I'll create a filter called no bedding. And for this particular filter, I will set the expression to everything that is not inside set 1. Just for comparison's sake, we'll create another filter, which is essentially its inverse, which is bedding only. And here in the expression, we'll set everything that is inside set 1. So right now, we are viewing the unfiltered data, but now let's take a look at the bedding-only filtered data. Notice that the contours are virtually unchanged from the unfiltered data set. The high density of poles in the center is really obscuring the significance of all the other data that we saw earlier in the vector plot. Now let's take a look at the no bedding filtered data. We see that after removing the bedding planes, the two orthogonal sets we identified earlier in the rosette plots now become apparent in the contour. Again, let's use sets from cluster analysis. And we will select the approximate centers of these two set clusters. And you'll notice that these form sets that wrap around to the opposite sides of the StereoNet. To visualize this a little bit more clearly, let's put in a StereoNet overlay on top of this. Show grid overlay, and we'll set the style to custom, and I'll put the axis orientation at approximately where these two set planes intersect. So that's at approximately a trend of 309 and a plunge of 74. Just through visual inspection, we see that these two sets are almost perfectly orthogonal. Okay, let's talk about reality checks when interpreting the data in this particular example. In summary, the first thing we did is we saw that we could only see the bedding data in the contours. So we checked the DIPS rosette plot and found convincing orthogonal joint sets. Then we do an extra check to see if indeed the bedding is obscuring the data by comparing the unfiltered data with the bedding only data. And we saw virtually no difference in the contour plot. So now that we know that the bedding is obscuring the data, we remove it. And of course, this is extremely easy to do with the DIPS filter option. After filtering out the bedding poles, we can actually identify the orthogonal sets. Finally, to justify to ourselves that this is not just a fluke, remember that this type of orthogonal set plus bedding structure is very typical of sedimentary rock formations. In this next example, we will see why kinematic analysis is such an important part of slope design. Kinematic analysis should be considered a routine part of domaining the discontinuity data. For a given set of kinematic properties, we can turn our attention to the region of poles or intersections that daylight, are steeper than the friction angle, and are within lateral limits. Using kinematic analysis, we can also identify the controlling failure mechanisms, such as planar sliding, wedge sliding, or toppling. So what happens if the controlling failure mode is governed by oddball discontinuities that are not easy to identify and lead to surprise failures? Remember that failure is not strictly governed by orientation. There are other factors that could contribute to failure, such as low joint shear strength or thick gouge. While kinematic analysis may seem like a numbers game, where the higher percent critical means a higher risk of a particular failure mode, we do have to be a bit careful here. The same number of problematic poles in a large set may be less important than in a small set, we cannot dismiss their significance simply because there are only a few. Many surprise failures are, in fact, caused by these rogue planes. The image here is pulled directly from Dr. Carter's 2018 paper titled Suggested Standards for Improving Structural Geological Definition for Open Pit Slope Design. Take a look at Figure 1A. This figure shows the raw mapping and drilling data. To the northwest and southeast are two distinct joint sets. Take a look at Figure 1B. For this particular slope, it would appear that the two joint sets control the wedge failure. However, when compared to Figure 2A, hardly any poles exist in the post-failure mapping, where the actual failure was controlled by planar sliding along the basal plane, as can be seen in Figure 2B. Well, hindsight is 20/20, but knowing what we know in Figure 2B, how come we totally missed it in the pre-failure analysis? Let's take a look at the diffs model we'll be working with. Here's the pre-failure data. The slope has a dip-dip direction of 55 and 245 degrees respectively. I've identified the two sets to the northwest and southeast. On the left, using wedge sliding kinematic analysis in dips, we see that the south dipping wedge sliding is the main instability risk. On the right, we have a pretty low percentage of critical poles in the daylight envelope, which would appear to indicate a low likelihood of planar sliding. So how do we amplify the flawed poles that aren't showing up in the daylight envelope, which was evident in the post-failure mapping? As previously mentioned, failure is not merely controlled by orientation alone. In this data set, we also have a bunch of quantitative and qualitative data we can use to help us identify what might be flawed. In particular, the thickness and 5-peak columns. In the aforementioned paper, there was an advanced weighting formulation applied to each pole based on several criteria, and then replotted with reweighted quantities to amplify the post-failure critical poles. We will be applying a similar concept, but we will cheat a bit by using filter options in dips instead. In essence, what we want to achieve is to give more importance to low peak friction angle and thick gouge poles by only showing poles with 5-peak less than 25 degrees and thickness more than 100 millimeters. So similar to the first example, we want to hide the dominant sets data so that we can see if there's any other data being hidden or obscured. Using the filter options, we will create a filter called low strength thick gouge. Under the expressions, we will query for poles that have a 5-peak that is less than 25 and with thickness more than 100. And we will not be considering anything that is inside set 1. And also anything that is inside set 2. Now let's look at a side-by-side comparison for planar sliding with unfiltered on the left. Let me change this to planar sliding. And then on the right, I will be showing for planar sliding the filtered data. And remembering that our filter data is everything that is not inside the sets and everything that has a low friction angle and a thick gouge. So what our filter is doing is it's essentially amplifying the flawed poles. We can see an approximate doubling in the percent critical as computed by the DIPS kinematic analysis for planar sliding after applying the DIPS filter. While 11.97% critical doesn't seem particularly high, remember that these are the highly problematic shear and fault planes with weak strength and thick gouge depth. Attention must be paid to the ones that fall within the daylight envelope. The first thing here is to look for the obvious kinematic failures using DIPS kinematic analysis and toggle between the different failure modes. And in this case, we identified wedge sliding as the most obvious failure mechanism. But our lesson here is don't forget to look for the less obvious. Weaker shear planes with thicker gouge are more likely to be unstable. So don't ignore these, even if they represent only a small percentage of the overall data. And as I demonstrated, we can easily query for these low strength thick gouge entries from the grid data using the DIPS filter. And finally, we perform further kinematic analysis in DIPS to see if these so happen to fall within a critical zone. So in this case, we checked the daylight envelope for planar sliding. And despite being few in number again, we definitely need to pay attention to any of these poles that fall inside that daylight envelope. I'm going to now pass it over to Dr. Trevor Carter.
Okay, folks, we've heard from Angela a good expose of the new features in DIPS. I've used more or less all of these techniques by hand in all the years that I've been working with StereoNets, using pieces of tracing paper originally. So I'm going to show you in the next slide, contouring is an issue in many cases. And I'm going to look at 4 problems here. Each one is something that we will look at in detail later on. So one of the issues regarding contouring is it hides data, as we have just seen. And when we look at our pole concentrations, we need to understand what the real data is. So looking at just the contours is an issue. Sometimes we have too much data, as we've been just looking at, and those are major problems. To look for the wood within the trees, we are looking for the rogue poles, and they often get hidden. Sometimes we sort things, as Angela's just been showing you, but we don't sort them with knowledge that there's some problems in the data sets. So we need to look at representative data to see whether what we are looking at is correct. So first, let's look at some problems of StereoNets and the good things that they can do. Summarizing information is superb. Angles are great, and we can get orientations. We can see the relationship between all sorts of the different discontinuities. We can see the patterns in the discontinuities, and we can demonstrate relationships between those and slopes. Our failure planes and wedge intersections we looked at just now with Angela, and I'm going to show you some of the problems that we see in a StereoNet that you don't see when you look at a real slope. We're looking at scale independence. So little wedges are just as important as big wedges, but we need to understand that in a real case as to what is the real requirement to understand wedge size. Key block concepts also are something that we may miss. And you'll see in here that some of the green areas, which are stable slopes, are retained because of a key block that's not failing. The total connectivity is assumed. In our StereoNets, all planes are equally big. The spread of the individual variability in poles is not really represented either, because a joint may have quite a lot of waviness. And last but not least, when we look at large wedges versus small wedges, the influence of cohesion is not taken into account. So these are issues that we have to think about very carefully. There's a paper by Steve Henscher, which is available on ResearchGate, which will outline some of these, and you can go and read that in more detail. But oversimplification of complex issues by contours is something that we've just been talking about. Often a problem that I've seen over the years is people pick too many sets in folded, real geologically deformed data. They're not different sets, they're just part of the same fold fabric, perhaps. We see all sorts of problems in beta orientation data from core because of lack of ability to follow the reference length all the way through. So I'll show you some of those. Angela showed you the issue with respect to low frequency data points, and missing key individual discontinuities with low shear strengths is a key issue that we must always bear in mind when doing work on a StereoNet. The friction cone we apply, very often we only assume the lowest value, but there's a positive influence of roughness, and we should look at a range of friction cones to see what is the control. And last but not least, the negative influence of water is a major player in slope stability. It can be analyzed on the StereoNet, and people have done it, but it's much easier to do it in limit equilibrium or other codes. So let's look at these 4 issues. To start with, let's look at some conventions. Contouring should really only be shown on an equal area net. Why? Because it's actually a density that we're trying to plot. We really want to have a visual of the dominance of zones on the net by eyeball. Equal angle projections were developed for crystallography, and they're great for those sort of uses, stresses, etc. But they shouldn't be used for contouring. These days, we've got very large data sets, and the spread of the data is huge. When we do Fisher distributions on that data, we tend to just smear it all together and we start to lose information. It was designed to help us when we only had small data sets. And it's something nowadays with drones and Cyrovision and all of these tools that we have, which are great, but we get so much data, we need to be filtering the other way. So let's look at this simple fold, and I'll come back to it. This is a girdle fabric. And if I plot this on an equal area projection, I get the true representation of what I've got if I have only a limited number of poles. Look at the difference between Greenland. The true size of Greenland with respect to Africa is illustrated on the right-hand side. An equal angle projection will over-accentuate what it looks like. In the same thing happens in your StereoNet. This is what the Fisher distribution does. It spreads the data out. And we talked about earlier the ability to look at your Fisher's K in your set data. So you can interrogate how much control, and you can actually reduce it in the analysis, if you will, and use Fisher. But I would recommend using Schmidt, which is direct and doesn't have any distribution. So those can be done easily in the StereoNet pull downs, and you can rearrange to use Fisher, and you get a slightly different looking net. So let's look at windows now. And we looked earlier at taking out the bedding data from the set that Angela analyzed. And this is something we always need to think about, but also think about the geology. So natural patterns always exist, but blast fracturing, because of the energy and the gas pressures, sometimes exploits certain fractures more than others. Stress in a tunnel or an underground operation will accentuate certain fracture sets. We saw on the presentation earlier, the orthogonal sets are very common with sedimentary rock, but in faulted and folded terrain and highly deformed terrain, Riedel fabrics are characteristic and something that we need to understand. So never use contoured nets alone. Always look at the plotted pole data, because you might be mixing things, especially when you're trying to domain things. So here we look at some natural fabric patterns. You can see on the right-hand side, the compressional regime of a fold accentuates extension fractures near the crest of the fold. And these will become something that you will see quite frequently in StereoNets. A complex folded and faulted pattern here, you have different nets resulting from the different areas of geological control. So when we use Televiewer data or we do core orientation, we basically are taking that data and plotting alpha and beta angles, which we must measure correctly, and plotting them on the net. But sometimes we get very oddball fabrics, which I'm going to call donut fabrics. And these are actually erroneous. This is a problem of Spancore. It's got nothing to do with the real data. We've got a number of tools that we use to collect StereoNet data and joint data, varying from simple hand tools, goniometers, through to more sophisticated. But these are also influenced by whether we are drilling at right angles to the fracture set. So sometimes we need to consider very carefully the orientation of where we place our holes so that we aren't making matters worse for ourselves. We need a reasonable angle of the joints so that we get good impressions from all of the orientation devices. And also, even that the core doesn't get spun by the driller. Ideally, in packer testing, we want to drill at right angles to a joint set so we can get a decent measurement of that individual joint set. So sometimes this compromises our ability to get good core orientation. So think about both when you're planning a drill program. There's some good advice in the DIPS files on the web. And the key requirements are getting contiguous, reliable reference lines, good alpha and beta angles, and here is what we need: a consistent on top or bottom of the core definition of where we put our reference line, always measuring it clockwise, looking down the hole. The number of data sets that I've seen where this has got screwed up, and that has complicated everything that's on the nets. There's even apps on the web that you can download to play with these. This is what Spancore looks like. Polished, it's got little circles on it, and it ends up on the net looking like this. That's not real data. And when we contour that data, we might even have picked joint sets and plotted these, and we said, okay, we've got a failure, direction of sliding, and all our analysis is wrong because we actually had a donut of wrong data. The Televiewer can help, but again, we have to be a little careful because most of the Televiewer information is used a magnetic orientation. So if you're in an iron ore deposit, be careful. Sometimes people log core and they log the fractures that are shown here as geological discontinuities. This is stress disking, and it shouldn't be plotted in your StereoNet, but I've seen that develop as a set within the StereoNet. We must be careful. So let's look. This is the old clay orientation methodology of packing a bit of clay into the bottom of especially a range core barrel. You can get any imprint of the core at the bottom that's remaining still within the borehole. And that's what you need for any orientation that's done without a Televiewer. So our orthogonal sets, we saw clearly that when we started, we had only the bedding obvious. The vertical jointing became evident if we use a rosette plot. And here is a clear 3 orthogonal joint sets. And this is what we're looking at. Here we've rotated them off horizontal, and that's what you commonly see in life. So first, make sure you just don't use contours. Always check the actual date. Use the rosette plot to see strike trends. Always look at the other poles to see what's left. Isn't it a different picture? So here's a situation where we wonder, is this a donut fabric? They're very unlikely. Basically, it represents a cone. Only ring dikes actually show this natural feature. So they are rare. So whenever you see a ring, ask yourself, is this a donut fabric? Check your data. See where the actual plunge of the drill hole is. Check the reference lines. Check all core for spun surfaces. Run ATV or OTV if you are uncertain and you have the ability to do so. But always be very careful and never put data together into big data sets if you've got lots of oriented core and you haven't checked to start with. The other issue with oriented core and with angled holes, any holes, is that you always end up with a zone where you don't sample too well. So is this a donut? Are we missing keep holes in that area? Again, check the orientation, check whether you can get another hole drilled to fill in some of the information in that data deficient zone. We can use Tatsagi weighting, but it doesn't help if the data's no good. We saw this earlier, classic fold fabric. This is plotting now just the crest of the fold. These get very complicated when we start to get faults involved, but I'm not going to touch that. These are some real folded situations. And here we have schistosity plotted as pole concentrations on the left and shears on the right. And there's a French word for this. And so we call these CS fabrics, and they're common in almost everything that we map. And in the middle here, we see folds, and we have the axial plane of the fold, and we have the fold axis. And we can interpret all of these things on the StereoNet. And these are real fabrics that don't have donuts in them. So this is what we're looking for. So if we take that bedding data and we fold it in a girdle at 15-degree intervals, right the way across the net, we can create a fold, a very simple fold. And then let's look at the area of a fold that gets dominated by fracturing. So here we are. our fold, and we're just going to take out those 4 particular sets. And there's our full fold fabric. And here's the filtering, which Angela showed you earlier on a scatter plot. And there's the contour net, which we end up with from that fold, just for the most intense fracturing. So would you have defined 2 joint sets? But now you know it's a fold. So these are things you need to be looking for on the net. And you can do it in dips. There's a function for fold analysis. So use these tools. And I'll finish by just giving us another way that we can perhaps attack this problem of looking for the rogue poles. You can look at the daylight envelope, as Angela did, and you can see the right-hand side image here. The left-hand side image is for a 70-degree slope plane. So if you take this one and you take that larger one and just look at the poles within that zone, then you can start to do the same exercises we did earlier and then see shear strengths and wonder about what you need to use in analysis. So your daylight envelope here is for the true overall slope angle, and this was for a fictitious 70-degree slope. And now I'm going to pass it back to Angela for any questions.
If you have any questions regarding the information presented in this webinar, please feel free to type it in the chat. And as well, suggestions for features in dips are also welcome.
Dr. Carter, thank you so much. It was very interesting. There are a couple of questions for you. One, can Dr. Carter speak a bit more on Terzaghi weighing and when it would be applicable to use?
Terzaghi weighting really is to help you accentuate bias that you've got in your data. So for example, if you're mapping a slope face, and that slope face, you'll see all of the features that dip out of the slope much more clearly than you'll see anything that's parallel to the slope. So you map that slope face, and the best way is to actually map 3 slope faces, one orthogonal to each other, and then you can see all sets. But use the Terzaghi weighting to bring out the lower represented features that are parallel to the face. The same thing with core. In that zone that I showed you, which was the area with deficient sampling, you can use Terzaghi weighting to bring out some of the poles and concentrate in that area. And it's really a way of getting rid of the bias that you have in orientation data that you're collecting. I hope that helped.
Yeah, thanks, Trevor. Another question, how the blind zone can be defined or evaluated in dips?
You use the cone command within dips, and you plot yourself a friction cone, basically, that's at right angles to the borehole trend line, and define it as 10 or 15 degrees off axis of the, so you use the orientation of the drill hole as a pole, and you're basically plotting the cones, and a 15-degree angle is a reasonable number, 10 to 15 degrees off axis. So that picks up everything that's parallel to the borehole axis.
Great. Another question is, how do you deal with the incipient joints which plot as fractures, traces, but have considerable strength?
This is a very common problem with Televiewer data these days. People are picking, let's say, bedding planes that aren't actually broken, or foliation planes. you have to filter this information right at the very earliest stage of your data analysis so that you can identify in the actual raw data what are real and what are not. So in core logging, we used to and still do mark when you get core breaks due to the driller. You should also go through Televiewer data and sort out things that are not matched in the core with real cracks. And that's the best way of getting rid of that problem, because they will not break. But when you go to, let's say, a block caving situation where you need to understand these, then you need to have them described in your database as veins or foliation planes with high strength and mineralogy. So it's all in the data collection and analysis before you even get on the StereoNet.
Excellent. Last question, because of the time, also goes for you, Trevor. You talked about only using Fisher for smaller data set and Schmidt for larger data because of smearing effects. You also said one pole cannot fully represent the variability of actual joints. So smearing isn't really useful. Can you provide some guidance on how to achieve best representativeness?
Well, this is where one needs to look at the sample size. And if I look here, and this comes from an excellent paper that's referenced in Steve Hensch's 1985 paper about use and abuse of StereoNets, but it shows you the difference between a 100-point sample on the right-hand side and 1,000 or 2,000-point sample on the left-hand side, which is close to the true data. So these issues of needing enough to show you what you have is data dependent. So you need to take 300 or 400 poles is an ideal. 100 poles is okay. Much less than that, you're starting to run into problems. Much more than 2,000 or 3,000, and you're starting to get overlap that's so major that you're starting to lose clusters. So something in the 1,000, 3,000 sort of range is the ideal to be working with. Can you go to the next slide, please? So this shows you an old way that was used frequently to try and determine this range of when you got reasonably good data. And this comes from Hook and Bray, 1977 book. And on the left in the graph there, you can see at which point the number of data points is starting to become real and how big an zone of your joint you have to sample. In the top right-hand StereoNet, all those points are on one joint plane. And so that comes from sampling with a 100mm plate. As you make your plate bigger, you get more and more of a better average. That's the problem of dispersion that you need to capture. And you can use the Fisher distribution backwards to get to that sort of data. And when you plot this on the StereoNet, you can plot the spreads around each of the pole concentrations, but you can also do it around the intersection concentrations to look at problems for wedges and also toppling wedges and toppling planes. Next slide. So go and read Hook and Bray somewhere in around page 73, 74, and you'll see a pretty good expose of this, and have a look at Steve Hensch's paper. And I think that'll answer your question on how many poles you need.
Thanks a lot, Trevor. There are more questions. We will answer them, and we will send the answers by email to all the participants. And I will pass it to Angela to conclude.
Thank you, everyone, for your time, and thank you, Dr. Trevor Carter, for joining us today and imparting all your knowledge. Keep safe and enjoy the rest of your day, everyone. Take care. Bye now.